Okay, today we're covering the final challenge of Damn Vulnerable DeFi, which is the climate challenge. So let's go ahead and look into it. There's a secure vault contract guarding 10 million DVT tokens. The vault is upgradable following the UUPS pattern. The owner of the vault, currently a time lock contract, can withdraw a very limited amount of tokens every 15 days. On the vault, there's an additional role with powers to sweep all tokens in the case of an emergency. On the time lock, only a account with a proposer role can schedule actions that can be executed 1 hour later. Your goal is to empty the vault. All right, let's go ahead and take a look at the contracts here. So we're going to have a look at the vault first. This one isn't too complex. There's just a lot of getters and setters here. So we can see that this is the vault. I think it's initialized with this amount of balance, so that much ether. The withdrawal limit is 1 every 15 days. There's a new modifier called only sweeper, so it requires that the sweeper is calling it. And the sweeper is just an address that is stored in the state. You can see there's an initialize here where it's following the UUPS upgradable pattern. So if you don't know what the UUPS upgradable pattern is, it's essentially a way or a pattern that you should follow when you want to upgrade your smart contracts. And it uses this idea of proxies that are pointing at different logic contracts. So kind of similar to the previous one where you have your singleton contract, which is your your logic that you offload to, but you do it with a delegate call, so it happens within the context of your contract, which is the proxy. And if you want to upgrade it, you can go ahead and upgrade your proxy to point to a different address, so all the logic calls are located to the new logic address. So you can go ahead, and this is the initializer here. It transfers the ownership of this contract to be a new climber time lock contract. So this is going to be the other contract in this challenge. We'll have a look at that in a little bit. We can see that admin is going to be a part of the parameters here. Same with proposer and the sweeper. Sets the withdrawal time and the last withdrawal time step. Okay, so we have a withdraw function here, which is basically only the owner can run this. Make sure that you are less than withdrawal limit, and it's done within 15 days and all this kind of stuff. So that's the only time that you can withdraw. It's 1 ETH every 15 days. Sweep funds. Now this looks very, very, very juicy. So we have a sweep funds function which will essentially transfer all the funds of a particular token address to the sweeper. So this probably looks like the thing that we're going to want to run that's going to point towards the attacker address. So let's just keep that in mind. We have get sweeper, we have set sweeper, we have get with last withdrawal timestamp, set with last withdrawal timestamp. Set sweeper is internal, and this is only called in the initializer here. So it's not like we're going to be able to call that somewhere else. And then authorize upgrade. So this is essentially the what is required to upgrade this contract to a different contract, as in like the logic is different. Okay, let's have a look at the time lock. So we had the owner of this vault is this time lock contract address. Let's have a look at what this does. So it has something called like an admin role and a proposer role, which is the hashes of those two strings. It has an enum of an operation state and a struct operation, which is the ready at timestamp if it's known and if the operation has been executed. And we can see the delay is 1 hour initially. So in the setup here, we can see that it's setting up the role of the admin. So the admin of this time lock. So this is implementing OpenZeppelin's access control set of libraries, which just kind of allows you to have different roles. So we're going to set a role of an admin, set a role of a proposer. And then it's going to set up these roles. So we're going to set the admin to have the admin role. And we're going to set the admin to also be the address of this. So its own contract is going to be an admin itself. And Yeah, so the deployer who deploys this contract is going to be an admin, and then self-administration. And finally, it's going to set the proposer to be the proposer role as well. So let's figure out what this proposer role and all this stuff does. I'm going to skip over this for a second, and I'm going to show you the schedule and execute function here. So kind of the idea behind this is that you can schedule different actions to happen, and then 1 hour later, after that delay, you will be able to execute that action. So let's have a look at schedule. So schedule can only be called by the proposer role. So if you have the proposer role, you can schedule an action. Requires that the target, so it's got targets, values, data elements, and salt. So this is going to be, I want to execute an action. Say, for example, I would like to execute a function on the Climber Vault. So say I want to run set sweeper, if I could. Then all we'd need to do is in the targets, we'd have an address of the one that we want to interact with. The value is going to be how much ether we want to send with this transaction. The data elements is going to be the ABI call that we want to actually create. So that's going to be the function signature and all the parameters there. And then the salt is just some random salt to make sure we can't do any repeat attacks. So it does some, some regular checks here. It then retrieves the ID of this operation. So all these parameters here essentially get hashed together. So if we have a look at get operation ID, they all get hashed together, and that returns a unique ID for every unique set of operations that you want to perform. It then requires the operation state of the ID to be unknown, as in if this has already been scheduled, then it's already known, therefore we don't want to go through with it. If it is unknown, then they're going to go ahead and set the ready at timestamp to be the block timestamp plus the delay, which is going to be 1 hour. And then it's going to set the known to be true so that you won't be able to schedule this again up here. Pretty straightforward. But you need to be the proposer role to do this. So once it's scheduled and say an hour has passed, we can go ahead and look at how the execute function will work. So the execute function works by passing in the exact same parameters that you pass into schedule. This way you don't have to store this scheduled data on chain. And then it does the same kind of checks here, and it verifies that the operation ID, which is the same, using the same parameters, and retrieves the ID that way. It'll go ahead and then run the execute functions on each of the targets. So we'll go each of the targets, iterate through them, function call with value. This is the data they want to call it with, and this is the value they want to call it with. Then after it's been executed, it's going to make sure that the operation state, as in the ID of the state, is ready for execution. And so this is done... get operation state of ID. So we can see that is done up here. And this just essentially returns whether it's ready to be executed. So if it has already been executed, then return executed. If it's the ready at timestamp should be greater than the block.timestamp, then it's ready for execution. Otherwise, it's just scheduled. Or otherwise, it's unknown. So essentially, it's checking, has it been an hour? Is this a valid action to be executed on? And then if so, go ahead to the next one, and then it sets the executed ID on the operation to be true. Therefore, you won't be able to execute it again, stopping these replay attacks. So there's a lot to take in here, and it's quite a lot to do. How do we exploit this? Where is the exploits here? And this one took me quite a while, but we eventually got there. The main issue, right, is if we have a look at schedule here, we won't be able to do anything because if we have a look at who the proposer is, we can see that initially there's the deployer account, there's the proposer account, sweeper, and attacker. And the balance of the attacker is set to 0.1 ETH. They then deploy the function as a proxy. So again, following this proxy thing. So you have the proxy, which is deployed, which points to the singleton. This is using a hard hat method to do it. So it's using the contract factory for Climber Vault to deploy it as a UUPS. It does some checks here. It then initializes the time lock the time lock address. So it gets the time lock address from the owner of the vault and gets the contract factory for that, ensure everything looks good, and then deploys the token as well. So again, what do we need to do? Empty the vault. Excuse me. Okay, so how do we do this? Where's the exploit? The exploit is actually in the execute function. So anyone can execute what has been scheduled by schedule. We can't schedule anything because we're not the proposer, but we can execute anything. Now you may think, well, why is that useful if we haven't had anything scheduled yet? And the reason being is that it actually checks whether the operation that we have just performed is ready for execution after we have executed it, which means that we can execute anything on behalf of this time lock address as long as it has been scheduled afterwards at least. So this exploit would be possible if this line was up here, but because it's after this actual execution call, we may be able to do something funky here. So we can kind of start to think about how we could potentially exploit this. The first thing is that if we can get what we're trying to execute and we schedule what we're trying to execute while we're executing it, so once it's done, the contract is in a state where what we just executed is valid, then this line will pass. How do we do that? Well, the problem is you may run into recursive issues, right? So for example, ignore the proposer bit for a second. Say we just want to schedule a schedule, right? And so we go execute. Okay, so what target do you want to call? We're going to call on this own target, no value. We don't want to send any ether to it. But the data elements is we're going to call the schedule data. Okay, so what data is that going to be? Well, we're going to have the targets, which is going to be schedule, and that target is going to have the data elements of, it's going to be the schedule data. So it goes back in and then you keep going in loops and loops and loops and loops. So essentially, you are not able to schedule the data yourself because you run into this recursive issue and you need infinite data to schedule it. So that's not going to work. So we have to think of something a little bit different. Regardless, let's kind of think about, say it is possible, how could we do it? Well, the first thing that we need to do to schedule something is firstly make sure that we have the proposer role. Now, luckily, as in the setup here, we have self-administration. So we can set up the role for the proposer role to be the contract itself. So we can do that as an operation, a target. We're going to set it to ourselves and make sure we set up the role to be a proposer role. Cool, that's pretty straightforward. The next thing that we want to do is to schedule that change that we just made. The next thing that we want to do is we want to upgrade the other contract. Now, why do we want to do that? If we upgrade this contract to a different contract, remember this kind of proxy, and then it's going to point to a different logic contract somewhere else, right? If we control that logic contract, we can change everything, right? The state is maintained, but we can change the logic. So what if we deployed a new version of this Climber Vault contract that changes the set sweeper function such that it's public and we can then control who the sweeper is? So then after that, if we can control who the sweeper is, we can run sweep funds, and steal all the DVT tokens. Now, the problem is, so these are kind of like our 4 steps, right? Firstly, we need to make sure we have the proposer role. The second thing we need to do is ensure that we can we upgrade the proxy to a new logic address. The third thing is that we need to schedule that contract. And I believe there's one thing we were missing. The other thing that we're missing is that once it executes, it needs to make sure that it's greater than that 1 hour. Now, if we're all trying to do this in one transaction, as in schedule the transaction that we're trying to do at the same time, that's not going to be an hour, and we can't do that in one transaction. So the third thing that we need to do is update the delay. So there's a handy function that lets us do that here, and we update the delay to be 0. Therefore, when it does that check, it can see that, the delay is 0. So we just do whatever the block time is now, which is going to be now. Yep, that's good to go. So there's 4 main things: propose a role, upgrade the proxy, update the delay, schedule the action. Now, the only problem is that we don't have a way to schedule a schedule because, again, we run into those recursive issues. So how do we get around this? The way we get around this is by using a third-party smart contract to do the dirty work for us. So instead of scheduling the schedule, we have 4 calls. Change the proposer role, and the proposer role will be no longer the contract itself, but a contract that we control. So another contract. Update the delay, upgrade the proxy, change, call the smart contract that we just proposed to, getting married. What that'll do is when we call our smart contract, which is the 4th and final execute, we then have this ABI, and this ABI is not recursive because our contract is going to be super simple, and we can pass that ABI prior to calling the execute function into our smart contract. So we save the ABI, and then once we call the ABI, call our smart contract, the smart contract then calls schedule with the predetermined ABI that we have that we calculated, such that once this is complete and it goes to get the operation state, it has been scheduled, the delay is fine, we proposed it, it's all good, and we can go through. Finally, after that, because we had successfully upgraded the contract, we can go ahead and set the sweeper to the attacker, and we can sweep the funds. Cool. All right, so we've gone through the exploit. Let's go ahead and look at the contracts. So in this case, we're actually going to create 2 contracts. And the 2 contracts that we're going to be creating, one is going to be the exploit contract, which is going to be called after execute. And one is going to be the new proxy contract. So the first one that it's going to be called is going to be called attack timelock.sol. And let's take a look at this one. So essentially, in the constructor, we're going to need the vault address, the time lock address, the token, and the owner. We then have 3 functions here. The first one is set scheduled data. This is going to be setting the scheduled data that we need to have prior to calling execute. So those 4 functions, again, it's going to be set proposer, set delay, upgrade proxy, call exploit on our contract. So we can predetermine this before we start our exploit, and we're going to set the scheduled data here. Within the exploit itself, we create some empty data, which is with the length of how many calls that we've just created. So the 2.length, which is here. And so this is the scheduled data and the 2 data, right? Then we call the time lock to schedule this new, these function calls that we've just completed. Then once it's done, we just call set sweeper and then sweep the funds. Now, how do we do this? This is because it has that new function, the new logic address that we've just created. Now let's go ahead and see what that new logic address looks like. So it's going to be called attackvault.sol. And again, this looks exactly like the original vault, right? This is exactly the same, except for one main thing. And that one main thing is this set sweeper function here. And as I said before, we can just set that to be public. And so we can go ahead and run set sweeper, and then we can go ahead and sweep these funds. So in our exploit contract, we're going to go ahead and sweep the funds, and that is going to go send all the funds to this contract address, and we can just run a withdraw function to get all those tokens. So let's go ahead and see what this looks like in code. Again, the majority of this is done in the smart contracts, but it's also good to see how this is done. Actually, there's still quite a bit happens in the code. All right, so the first thing, again, as always, is to connect to the existing contracts as the attacker. So we're going to go ahead and connect to them. The next thing is to deploy our attacking contract. right? So this is what we require. So in the attacking contract, we need to provide the vault address, the time lock address, the token address, and then the owner address, which is going to be the attacker. The next thing is to deploy the malicious contract, which is going to be our new logic contract for the vault. So we just go ahead and deploy that. The next thing we need to do is start building out the ABIs for the 4 functions that we need to execute. So the first thing is we need to calculate the proposer role, which is done through a hash. We have a helper function, which is going to help us create the ABIs. And these are the 4 functions here that we're going to do. So in this create interface function, we just require the signature, the method name that we want to call, and then the arguments for that method name. So this goes ahead and creates the new Ethers utils interface using the ABI. It encodes that function data using the method name and the arguments, and then it goes ahead and returns that. So we can see again, these are the 4 functions that we need to execute. Set the attacker as the attacking contract as the proposer for the time lock. So we're going to go ahead and run grant role with this role and this account. We want the proposer role, which is what we set up here, which is the hash of this string here, and then to be the attack contract.address. Once that's done, we want to update the delay to 0. Again, run update delay on update delay with a value of 0. The reason this is in brackets is all arguments are in brackets here. That's just what my function requires. Here. Then we want to call to the vault to upgrade the attacker to the attacker control logic contract, which we've just deployed. So this is done through an upgrade to function with just a simple address. Again, upgrade to our malicious vault contract address. The final thing is to call our contracts exploit function, which is here. And this exploit function will go ahead and schedule the data schedule the functions that we've just created. And that's it. Then all we need to do is get all these and add them to an array. So we have the 4 functions and the 4 data. So the to address and the data. So attack time lock, grant role data, and these are all aligned. Now that we have the ABI, right, again, removing ourselves from that recursive kind of constraint, we set this scheduled data. This ABI is going to remain the same. Because it's all premeditated and pre-calculated, we set the scheduled data and store that in our contract before we even do the execution. Finally, now that we're all ready to go, we can go ahead and execute the 4 calls. So we go ahead and go to our attack time lock as the attacker, execute the to address with the array of data.length of fill 0, which is basically the values that you want to send, the data which is we added here, and then here is the, I think that's is that the salt? Yeah, that's the salt. So just some random 32 bytes for the salt. So again, this is going to go each do of these function calls, and then in our exploit function, we're going to go schedule these 4 function calls that we've just created such that we pass that final check. Finally, once we've done all that, we should have swept all the funds, and all the funds should be in the smart contract that we've deployed, and we can go ahead and run attack contract.withdraw. And that's it. So let's go ahead and run this and see if we have completed it. Fantastic. So you can see there that we have passed this challenge. So I hope you guys enjoyed this and learned something new. This one was very, very tricky. It took me a really long time to get around the kind of recursive constraint without thinking about how to use the smart contract. This leads us to the end of the Damn Vulnerable DeFi series. I hope you guys have learned something. I definitely learned a lot going through this series, and I will catch you guys in the next one. See you later.